So non-steady state problems, let's just define some concepts that go with this, some ideas that are going to help us like kind of wrap our arms around what we're supposed to do, and then we'll get into the actual formal analysis on this. So non-steady state problems, the idea is that temperature and heat transfer Q dot can vary with time. Can vary with time. So that is to say temperature can be a function not just of like X, Y, or Z, but also of time. It's just a definition of a non-steady state problem. I mentioned this term like lumped capacitance. So lumped capacitance means a specific subset of a non-steady state problem. So if we wanted to think of like the simplest possible representation of non-steady state, we could basically get rid of all of these. Right, say these are uniform or unimportant, right? There's no significant change. And we're going to say temperature is only a function of time. So this is lumped capacitance. And what is this actually saying? It's saying that the temperature in the body that I'm modeling has no spatial variation, but it has temporal variation. So think of like, we'll get to an example, but think of like a metal sphere, like a BB or something, some shot, right? It's like metal, so it's very conductive. Maybe you put that in a liquid bath. The entire thing is kind of changing, but there's not a temperature distribution inside that thing, right? It's just a uniform temperature. So this is the idea, so we're going to kind of go with this. So lump capacitance, let's just say this is uniform temperature in space, but not in time, right? So this is, in other words, this is a 0D problem. If you're a physicist, you might argue with the idea of 0D because time is technically a dimension. But for us, we normally think about spatial dimensions as dimensions. Time is sort of the other component, right? The odd child. So decide whether there's any significant temperature distribution. Well, we can go back to the same ideas that we used for extended surfaces, right, where you have this ratio of resistances, and we can apply it here. Right? The same ideas apply. If we can prove that there's really no significant temperature drop inside the body relative to the surroundings, then it's effectively a 0D problem. Right? So we can define again this Biot number. So we would say Biot number is, again, it's just R conduction internal over R surroundings. And we want that to be less than 0.1. That's our cutoff. I'll say again that if you decide that like that's not accurate enough, you can certainly adjust that. But this is a rule of thumb. All right, so how do we estimate these things? Now, normally for lump capacitance problems, you're going to kind of not have a nice, neat geometry to worry about. Like you're trying to neglect temperature gradients inside this thing, maybe because the thing itself is kind of weird shaped, or like it's hard to do analysis on it. Maybe it's a sphere, maybe it's a person, maybe it's something else. So you don't really want to worry too much about the specific lengths involved. You just kind of want some estimate. Write out generally what I mean here. So first, let's write R conduction internal. So that's normally just L conduction over K A conduction. So what I mean is changing the terminology a little bit, but it's the distance you have to conduct, L conduction, over the conductivity times the area available for conduction. So again, for these odd-shaped bodies, maybe it's not clear what L and A are. So there's a good approximation you can use, and I think some of you have found this already for the extended surface. But it's basically to say L conduction is equal to the volume of the object over the surface area of the object. So as long as you can estimate those two things, this is a pretty good approximation for the average or effective length that heat has to conduct to get out of the system, right? So we can take this, plug that in. A conduction, I guess, again, is a little bit hard to decide on, but we can always say A conduction is surface area. That's a pretty good approximation. All right, so we end up with plugging these things in. We might say, let's do a specific example. So for a sphere, we would say L conduction is equal to volume over AS, so that's 4 pi r cubed. So let's call this r out cubed over 3. And then, see, 1 over surface area is going to be 1 over 4 pi RO squared. So this is actually just RO over 3. All right, so the conduction length for a sphere is just R over 3. I guess that kind of makes sense, right? The bulk of the material in a sphere is kind of close to the shell, just because the volume is growing as you go out in radius. So this would be a pretty reasonable approximation. Again, surface area would just be the surface area of the sphere. So you just plug this in and compute the Biot number. For this, it ends up being, Biot number is, let's see, so it would be RO over 3K AS, H bar AS over 1. All right, so this is internal conduction times the resistance to the surroundings. So if you had like radiation resistance, or maybe your sphere happens to have like a shell around it, and there's contact resistance or something going on, like all of that can factor in, as you saw in your homework, hopefully saw in your homework. Here, this is just taking the product of conduction internal, which we just decided the length scale, times the surroundings resistance, which would be the total resistance. For this case, if it's just H bar, then this ends up being RO times H bar over 3K. Right? So this, for a sphere, would be the Biot number calculation you would do. If this happens to be less than 0.1, then good. It's a valid 0D assumption. Questions on this? Okay. All right, so again, like the same ideas apply here. You're just trying to prove that something's unimportant relative to something else. And why are we doing that? So that we can neglect any spatial temperature variation and just say that the body temperature is changing with time uniformly, right? There's a uniform temperature internally that's changing with time. All right, so let's give a little bit more concrete example here.